Have you ever really stopped to think about how that little device in your pocket actually thinks? It's not magic, not at all. In fact, it's all built on a set of rules so incredibly simple, it's kind of mind-blowing. So let's pull back the curtain and uncover the logic that's hiding right there in plain sight. Okay, just think about this for a second. You flip a light switch, right? And boom, the light turns on. Super simple cause and effect. But then you tap a tiny little icon on your phone and a whole universe just appears. Information, friends, entertainment, it's all right there. Now, both of those things use electricity, but they are worlds apart. So what is the real secret sauce happening behind that screen? Well, the answer really starts with this fundamental split. We've got to get our heads around the difference between devices that are built to do physical work and the ones that are designed to handle information. So on one hand, you've got your electric devices. Their whole job is to take electricity and turn it into something physical. The motion from a motor, heat from a heater, or light from a bulb. It's all about brute force, really. But then on the other hand, you have electronic devices. And these are the brains of the operation. They're carefully, precisely manipulating electricity to process information, to follow instructions, and even to make decisions. Let's put it this way. In the electric corner, you have the heavy lifters. Things like motors, big industrial heaters, your basic lighting systems. And then in the electronic corner, you've got the thinkers, the sensors that see the world, the control boards that tell everything what to do, and of course the microchips that do all the heavy, mental lifting. All right, so if electronic devices are all about information, then how in the world do they actually do it? What's the one tiny little component that lets them think? Well, let's dive right in and meet the microscopic hero of this entire story, the ultimate switch. Okay, so the magic all starts with these amazing materials called semiconductors. The most famous one, of course, is silicon. What makes them so special? Well, we can actually engineer them to either let electricity flow through or stop it dead in its tracks. This gives us incredible, precise control. It's not just a simple on or off pipe. It's more like a programmable gate for electrons. And the one device that perfectly harnesses the semiconductor power is the transistor. It's this tiny, elegant little invention, and honestly, it is the fundamental building block of our entire digital world. Everything, and I mean everything we're about to talk about, starts right here. Now, the transistor really has two main jobs. It can work as an amplifier, to boost a weak signal. But its most revolutionary role, the one that makes your phone smart and your computer compute, is its job as a switch. By turning a current on or off, it can represent the two digits of the binary language, a 1 for on and a 0 for off. This is the key. Okay, so we've got a tiny switch that can stand for a 1 or a 0. Big deal, right? Who cares? Well, the real genius isn't the switch itself, it's what happens when you combine them. Let's see what happens when you start arranging these things into circuits that can actually make simple decisions. And these little decision-making circuits, they have a name: logic gates. A logic gate is basically a tiny little machine. It takes in one or more electrical signals, those are the inputs, and then it spits out a single output. And here's the cool part. That output isn't random at all. It's determined by a very specific, unchanging logical rule. This is really the first baby step towards actual computation. And get this, while there are lots of different kinds of logic gates out there, almost all of them are built from just three super simple foundational types: the AND gate, the OR gate, and the NOT gate. Think of them like the primary colors of the entire digital world. So how do these things actually work? Let's dive into the basic rules of logic. And seriously, prepare to be amazed, because the amount of complexity we can build from these three simple ideas is just staggering. First up, we have the AND gate. And this one is the strict one. It's the tough one. It will only, and I mean only, give you a true or a 1 on its output if all of its inputs are also 1. The logic is right there in the name. For the output to be true, this input and that input must both be true. And this truth table here lays out every single possibility. So if input A and input B are both 0, output is 0. If one is a 1 and the other is a 0, still 0. The only time, the only way you get a 1 on the output is when input A and input B are both 1. That's it. No exceptions. All right, next up we have the OR gate. And this one is way more relaxed than the AND gate. The OR gate will give you a 1 output if at least one of its inputs is a 1. It doesn't need everything to be perfect. Just one is enough. The logic is this input true or is that input true? If so, we're good to go. And its truth table tells the whole story. Look, the only way you can get a 0 out of an OR gate is if all the inputs are 0. If input A is a 1 or input B is a 1, or hey, even if they're both 1, the output is always going to be a 1. It's a much more, inclusive gate. And finally, we've got the simplest one of all, the NOT gate. People often call it an inverter because, well, that's literally all it does. It takes one single input and just flips it to its total opposite. It's kind of the rebel of the group. The logic couldn't be simpler. If a 0 goes in, a 1 comes out. If a 1 goes in, a 0 comes out. That's the whole thing. Okay, let's recap. We have these tiny transistor switches. We combine them to make logic gates that follow these simple rules: AND, OR, and NOT. So now, let's zoom all the way back out and see what happens when you take this simple idea and scale it way, way up. It's time to build a digital brain. And this is where it all comes together. See, the transistors are the switches. You group them together to make the logic gates that make the simple decisions. And then you take vast, vast networks of those gates and etch them onto a single tiny chip, and that becomes an integrated circuit. That's the brain inside every single electronic device you own. So what kind of scale are we really talking about here? How many of these little transistor switches do you think are in a modern computer chip? The answer is billions. Yeah, with a B. Billions of them all packed onto a tiny piece of silicon, smaller than your fingernail? I mean, just let that sink in for a moment. Every single complex thing your device does, from editing a photo to streaming a movie to connecting you with someone on the other side of the planet, it all just boils down to billions of incredibly simple and, OR, and NOT decisions, all happening at speeds we can barely even comprehend. It's the ultimate example of true complexity being born from absolute simplicity. So the next time you pick up your phone, just remember the logic that's sitting there in your pocket. It all started with a single switch that became a simple gate that then became billions of them working together to create a kind of intelligence. And it really makes you wonder, right? If these simple, elementary rules of logic built the entire digital world we live in,